Okay, good afternoon. So mine is the first session after lunch. So I hope the lunch is not lunch was not too heavy. Uh, it, my presentation is a bit technical, so I would like to make it as interesting as possible, just to avoid the boringness. So the topic is maximization of feed rate and reduction of CO2 emissions in integrated VGO and diesel hydrotreater. So basically, I am a refinery man. I come from India. I work for Hindustan Petroleum Corporation Limited, based in Mumbai. So agenda of my presentation will be, I will talk briefly about my company. Then I will have a brief detail about the unit in which we did some innovations and uh, feed maximization. Then I will dive deep into our first topic, that will be throughput maximization. Then uh, I'll discuss about energy optimization measures, basically the CO2 reduction initiatives which we took, and we were able to save a lot of energies and also CO2 emissions. The what? And I'll finish with the summary and the way forward. So basically talking about my company, HPCL, that is Hindustan Petroleum Corporation Limited. It is one of the major PSUs of India. It is one of the Maharatna of India. Basically, we have got two refineries in the India as of now. One is based in Mumbai, that is having a capacity of 9.5 MMTPA. Another one is in Visakhapatnam, that is having a capacity of 15 MMTPA. We also have joint ventures with Mittal at HPCL Mittal Energy at Bhatinda. We also had joint venture at Mangalore Refinery. We also have a upcoming refinery in Rajasthan, which is in joint venture with Rajasthan government. So total JVC is around 35.3 MMTPA. So if I talk about Mumbai refinery, it has got around more than 29 units. It's a complex refinery. It is having almost a lot of units, two FCCs, two hydrotreaters, CCRs, isomes, etc. So I have already discussed this. Mumbai refinery having capacity of 9.5 MMTPA. Our Visakhapatnam refinery has got 13.7 MMTPA. Yeah, one major thing about Mumbai refinery that we are the one of the largest producer of lube oil. So we have 428 TMT of lube refinery at Mumbai. We have a well-established R&D center at Bengaluru. We have around more than 500 patents on our name. HML refinery, I have already talked about. MRP also, I have already discussed. So I will just talk briefly about the unit, which is basically where we did some experiments and we maximized the capacity. So basically, this is DHT means diesel hydrotreater. So it is an integrated one, means we can process VGO means vacuum gas oil also as a feed. Basically, the raw feed is raw diesel. So if I talk about the capacity was around 2.2 MTPA. Basically, this unit was commissioned was in the year 2013. Then it was revamped in the year 2020. And in the revamp, we made two major changes, but the capacity remained the same. So revamp design has got two modes of operation. I'll talk in the later slides. So the feed VGO section design feed is around 176 meter cube per hour. Just we can mark these numbers because I'll talk about these numbers also. And diesel section feed is around 150 meter cube per hour. So specification, as we all know, diesel, we have to anyway produce the diesel which is having less than 10 ppm sulfur. VGO product which we are producing from the unit is less than 500 ppm, and it is not the finished product. This VGO again goes to some other secondary processing units. Diesel feed, as is obvious, basically comprises mainly from diesel streams, raw diesel streams, from crude distillation units, and it also has light cycle gas oil from FCC. VGO feed definitely consists of VGO streams from CD1 and 2. So if I talk briefly, if I'm able to make people understand this. This is basically a brief schematic of the unit. Yeah. So if you can say there are two reactors which I have shown as R1 and R2. So basically the reactions is being carried out in these two reactors. So as I was talking that we can process two kind of feeds. So basically these reactors are being operated in parallel. As you can see, this reactors goes steam goes separately, and the feed to this reactor, this steam goes separately. So in this reactor, we can process VGO also as a feed, or we can process diesel also as a feed. But in this reactor, we can only process diesel as a feed. So this is why this unit has been named as integrated VGO, because it can process VGO also. Also, there are two modes of operation. When we have diesel in both the reactors, it's called diesel only mode. When we have VGO in one reactor and diesel in this reactor, it is called VGO co-processing mode. Uh, Other configuration is similar to what we have in our hydro treating units. We have hot separator, we have hot flash drum. Then after that, I have not shown. After this portion, basically the section is stripping and fraction section. So my first topic, that is throughput maximization. So as I discussed in previous slides, the unit design feed is 326 meter cube per hour, and I'm happy to announce that we were able to achieve a feed rate of around 410 to 412 meter cube per hour, which is around 125% of the design feed. So why we choose to increase the diesel feed? Because the diesel cuts was having a very high profitability. Diesel cut prices were very high, and it was need of the hour to maximize the diesel feed. So for this, we went through a lot of plannings, lot of discussions, and design considerations were also chosen. Were also thought process was given to them, whether the unit is designed, whether the control valves are designed, whether the compressors are designed, whether the all the rotary equipments or other safety equipments, whether they are designed to handle that much feed. Then the third point, since we were increasing the feed of our secondary unit, so it was also necessary that we just made the additional raw feed available for this unit. So definitely we'll have to make changes in our upstream units also, so that we can have the sustained operation of that high unit capacity. So diesel production, we were able to increase it from 234 TMT to 339 TMT. Also, as I mentioned that we have another refinery at Vizag. So we also utilize this opportunity, and in Vizag refinery, there were some issues in diesel units. So we also brought 330 TMT of raw diesel from Vizag to Mumbai and processed in our unit. So definitely, as it is obvious, we were going very slowly, and so slowly first we increased the feed up to 350 meter cube per hour, and obviously there were a lot of issues, hurdles, which we tackled all of them. I will discuss about them in the later slides. So after achieving 350 meter cube per hour of feed rate, uh, we gathered the observations, and we had to make certain changes because we had a lot of issues for increasing further. So first we troubleshooted all those issues, then we further increased the feed gradually, very gradually. We also monitored parameters of critical equipments, and any limitations were also investigated. Equipment monitor was very critical and necessary, because we were not sure if like the equipment will be designed for that high quantity of feed. But we were lucky enough that we did not find any challenges in terms of equipment or any control or anything about that. So now coming to the important part, that is roadblocks and challenges. So first one was high auto backwash filter frequency. So it's a it's a bit technical. So in the feed line, in the cold feed line, we have feed filters which are auto backwashing type. It means depending on the delta P, they automatically go into the auto backwashing mode. And since we were increasing the cold feed, so this auto backwashing frequency had gone up. So what was the issue due to this high auto backwash frequency? That the auto backwashing liquid again mixes to the diesel product, and the auto backwashing liquid is raw diesel. So the raw diesel was mixing with the product diesel. So that was creating issue in terms of sulfur content of the finished diesel product. We were every time this auto backwash happens, we always observe a peak in the sulfur of uh, diesel pro sulfur. So this was the issue, and we were able to resolve this issue by minimizing the cold feed in the unit, because the unit has the option that unit can process cold feed also, and unit can take hot feed from the primary unit directly. So we minimize the cold feed and we maximize the hot feed, and this issue was automatically resolved. Second one was frequent cold feed pre-filter plugging. So like auto backwash filters, we also have pre-filters in the feed lines, and this issue was also resolved when we maximize the hot feed. Third one, which we faced, was the density and viscosity of diesel product. We observed that we were running very close to the specified density and viscosity. So for density and viscosity, as you know, the only thing which we can do is to make changes in the feed. So we made changes in the raw feed itself. We made the feed a little bit heavier side, and we were able to resolve this issue. Fourth one is increase in fuel gas consumption. So obviously, when we are increasing the feed and we are going above the design feed, the fuel gas consumption was bound to go up. And to resolve this, when we maximize the hot feed, slightly this issue was resolved. I will discuss a little more about this when I talk about the energy consumption, energy reduction measures. But we also optimize some gas to oil ratio in diesel hydrotreater. There is a term called as gas to oil ratio. It means we have to maintain a certain ratio of fuel recycled gas, that is hydrogen, as with respect to the feed. So we optimize that, and that helped us reducing the fuel gas consumption. Fractionator, as I discussed slightly, that we have stripping section in which we have fractionator. So what does fractionator do? Basically, diesel, after going into the reactors, diesel finally goes to the fractionator, where the naphtha content, the kerosene content is taken, is separated, and from the bottom, diesel is taken out. So when we increase the feed, we observed that a lot of flaring was observing from the fractionator overhead. So flaring, as we know, is a loss to the refinery. So it was to be minimized. So we made some changes in the fractionator operating conditions. We reduced the bottom pressure. We reduced the shipping steam without any loss to diesel product flash point, and we were able to make the flaring from fractionator as zero. We have a mine scrubber. It means because in the reactors, the reactions are happening. So in those reactions, H2S is getting generated. So that H2S has to be taken out, and it is to be taken out by the amine. So we have amine scrubber. So we also observed that a lot of flooding was there in the amine scrubber after we were increasing the feed. And this issue was resolved when we optimized, or when we reduced the recycled gas flow to the reactors while optimizing the gas to oil ratio. Catalyst deactivate. This was actually not a challenge, but a bit of concern, because when you increase the feed, you have to maintain very higher temperatures in the reactors. So WABT of the reactors goes up. So that poses a challenge. So that it may happen that catalyst may lose its activity at a very faster rate. But we observed and we checked with the help of our technical department and R&D department, and it was found to be under the prescribed ranges only. Mechanical integrity of the unit was like one of the greatest fear in our minds when we were increasing the feed. So at each and every steps, what we did, our inspection department did the thorough inspection of the lines in terms of vibrations or any mechanical integrity of the unit, and it was found okay. So the constraint limitation and measures I have already discussed. I'll skip the slides. Okay, now coming to my second topic, that is energy optimization strategy. So energy optimization can be divided into four parts. First one is no capital investment. So when I say that no capital investment, I mean to say is that, see, licensors and designers give us some certain conditions, and on the basis of those conditions, we have to operate the unit. We have to maintain those conditions, and we normally do not like make any changes in those conditions. But what we did, based on our observations, we made certain changes. So we did not do any capital investment. Rather, we made some changes only. And on the basis of those changes only, we were able to do around 12 plus initiatives. And all these initiatives were result oriented. So we had, for each and every initiative, we had tangible benefits. So I'll discuss in the later slides. So the 12 plus initiatives can be categorized into the 5 parts. First one is combustion and heat optimization, where mainly I'll discuss about how we reduce firing into the furnace. Second one is process integration and heat recovery. It means where we were able to achieve the heat reduction, energy reduction by doing some integration or by doing some changes in the hot feed and cold feed. Then hydrogen and gas management, wherein I will discuss about the gas to oil ratio optimization. Then fourth one is utilities and steam optimization. So our unit is a big unit, so it it uses a lot of steam and other utilities also. And if we can, or if we can save some steam consumption, so it definitely, it is like saving some energy consumption only. Equipment efficiency. So I will talk about some equipments which were not operated efficiently. We made some changes and were able to achieve greater efficiency of those equipments. So under combustion and heat optimization, so our unit has got two furnaces. Basically we use furnace for heating the feed, because we have reactors, and in reactors we have to maintain certain temperature as well as pressure conditions. So to maintain temperature in the reactors, we have furnaces. DHT unit has got two furnaces. One is for reactor 1 and other furnace is for heating the feed to fractionator. So we were able to reduce the fuel gas to furnace F1002 to 0. It was one of the major initiative which we took to reduce the fuel gas consumption, to reduce the CO2 emissions to the atmosphere. And see, basically what we observed and thought, that in the fractionator, what we are doing, we are just separating the naphtha and kerosene, and ultimately we are mixing the kerosene again to the diesel product. So we had a close watch on the diesel flash point while we were reducing the fractionator bottom temperature. So we were able to achieve a certain point wherein we were able to shut down the furnace completely. And one thing which also helped us, that this both F1 and F2 have got the common convection zone. So even we did not fire anything in F1002. The F1001 gases were anyway coming, flue gases were anyway coming to the F1002, because convection is through F1002 only. So we were able to cut down the furnace fuel gas to 0, and we were able to achieve the energy reduction. Diesel flash optimization, as I talked, we observed that diesel flash, we did not have any issue in the diesel flash. So this is the trend basically. As you can say, fuel gas consumption in the fractionator inlet temperature. So basically, if I talk about the fuel gas, we were able to save around 450 normal meter cube per hour of fuel gas. That comes as 9,440 tons of CO2 equivalent. So talking again about combustion and heat optimization. So we have Keros chipper. For Keros chipper, we have reboiler. And for kerosene, we have two modes of operation basically. We have one thing which we call as HPCK, that is HPCL compatible kerosene. So between diesel and petrol being sent to the marketing, the pipeline has to be filled with HPCK. So we also observed this thing, and we observed that when the unit was not on HPCK mode, so why to waste the energy in the kero reboiler? So we reduced the reboiling, and we were able to optimize we were able to save around 880 SRFT per year. Second one is heat optimization. We made some certain changes in the VGO preheat. We basically have preheat chains, and we were able to save around 120 nm cube per hour of fuel gas. Third point is combustion air in TTO. So what is TTO? We have also sulfur recovery units. So TTO is basically the tail gas thermal oxidation. So we also observed that in TTO, the excess air which was being maintained was around 10 to 12%, because the licensor has asked us to do so. But when we then again reduce it from 12 to 5%, and we were able to reduce around 440 SRFT per year. So this approximate saving comes around 2,105 SRFT per year. Now talking about the process integration and heat recovery part. So as I discussed, we maximize the hot feed, and maximizing hot feed not only resolved our issue of feed filter and auto backwash filter plugging, but also it gave us a lot of benefits in terms of energy reduction. So what it did actually, in outcome is increase in VGO train preheat temperature from 135 to 141, increase in diesel train preheat temperature from 105 to 112. So the feed charge heater, as I discussed, we are having two heaters. So one heater, CIT means the inlet temperature went up from 229 to 233 degrees C, and fuel gas consumption reduced by 165 nm cube per hour. So our approximate saving comes around 3,456 tons per CO2 equivalent. So this is what I discussed. This is the cold feed flow, the unit we were maintaining here. Now we reduced to here, and our furnace CIT went from here to here. So gas to oil ratio, as I discussed, we have to maintain a certain gas to oil ratio, means we have to maintain a certain flow of gas, that is hydrogen gas, to the reactors as compared to the diesel feed. And we normally maintain it on higher side. We do not give a lot of attention to this, because we are always in the fear that if we maintain on the lesser side, maybe our catalyst life may get affected. But we again did a very good optimization here. We reduced R1 gas to oil ratio from 620 to 460. For R2, we reduced from 910 to 800. So basically what it is doing, when we are reducing the recycled gas flow, so we have recycled gas compressor. That is a very big compressor. It is a 7.6 megawatt compressor. So it takes a lot of energy. So we were able to reduce the RDC amps by 40 amps. Also, when we reduce the recycled gas flow, this recycled gas flow again is going to the heaters. So we are also getting benefited by in terms of fuel gas consumption. So the total approximate savings comes around 5,920 CO2 tons equivalent per year. Stripping steam optimization. So as I already told that we use a lot of stripping steams in the strippers. We have strippers, we have fractionators. So on the basis of product specifications, we reduce stripping steam to our strippers, diesel and VGO strippers, from 1,600 to 1,100. We reduce the fractionator stripping steam from 2,500 kg per hour to 0. That was a huge reduction of stripping steam. And see, because we noticed that there was no issue of maintaining diesel in flash, so we were able to reduce diesel. We also have a savings of 84 tons per day of steam uh, if we add all those two in the point number 1 and 2, so this comes around 84 tons per day of steam savings. That is 1878.8 SRFT per year. So approximate savings, including flare loss, comes around 6,400 tons CO2 equivalent per year. Again, SWSU means we have one other unit, that is shore water stripper unit. So it only has a tower. In the bottom, we have reboiler, we have steam to heat in the bottom. Basically, shore water means the water which is having H2S. So we have to remove H2S out of shore water. So we have to maintain a certain top as well as bottom temperature in this tower to remove all the H2S from the shore water. So what we did, we increased the pump around temperature from 65 to 75, and this 10-degree delta reduced the steam from 4,800 to 2,700 kg per hour. TGCU, we also have, as I told, SRU units. So SRU, we have tail gas cleanup units. So here we reduce the mine circulation from 32,000 to 17,000 kg per hour, and we were able to achieve a steam reduction by 800 kg per hour. So all these total initiatives helped us achieving a reduction of 4,867 CO2 tons of CO2 per annum. In the last talking about equipment efficiency, we observed that there were some AFCs, means air fin coolers, which were not required to run at the high speed or at the full speed. So we provided VFDs to those AFCs. We also observed that in our ARU, means the mine regeneration unit, one AFC which was giving only 1 degree delta T across it. So while it was taking around 14 amps, so we just stopped it. So in this way, we increase the efficiency of these equipments. So summary, we were able to achieve a unit feed rate at 125% of the design. In terms of SRFT, we were able to achieve around 11,938 SRFT savings per annum. In terms of tons of CO2 emission reduction, it was around 38. Hydrocarbon losses were also minimized by minimizing the flare losses from fractionator. Way forward, so maybe we have to sustain this increased feed rate and continuously monitoring the critical equipment to ensure reliability and performance. And maybe we can see if we can go further on the feed. Operational challenges, so we'll have to implement solution for frequent auto bypass filter frequency and cold feed filter plugging. We'll also enhance mechanical integrity and address any recurring issues in the unit. In terms of energy optimization, further, maybe we'll have to see the further reduce fuel gas consumption and maximize hot feed uses. And we'll have to continue to optimize gas to oil ratios and stripping steam uses. In terms of cost reduction measures, we'll have to minimize hydrocarbon losses by improving operation controls and process adjustments. We'll also focus on reducing naphtha export and increasing diesel yield. Performance monitoring and troubleshooting, maybe we'll have to regularly review and analyze operational data to identify potential issues early. For future enhancement, basically, maybe we'll have to explore new technologies and process improvements to further increase efficiency and output. And we'll also plan for further increasing the capacity based on the available diesel feed. Thank you. I'm open for any questions.